Condensed matter can be hard or soft, organic or inorganic, liquid or solid. Research is undertaken in all of these arenas in the NC State Physics Department. One faculty member whose studies are pursued on campus and at national laboratories is Professor Devine Kumar.
My research strengths are in creating new materials and studying their atomic scale structures. So I do a lot of work at the Argonne National Lab outside of Chicago and the Advanced Light Source at Berkeley in California, and also the Brookhaven National Lab in Long Island, New York. So we characterize our samples using a wide range of techniques available in the department. We have an atomic force microscope, which enables us to image the surfaces of the films which we grow, where you can actually see the atomic steps on the surface of these materials. We also have an X-ray diffraction system, which enables us to do diffraction of very thick films which we grow. We also do transport and magnetic measurements, and we have a system in the department which enables us to measure these properties down to the Kelvin, single Kelvin, millikelvin range. I'm bringing a new tool which will enable us to grow new materials one atomic layer at a time, using this system called the molecular beam epitaxy. Kind of like Lego with different colors of blocks. So you have red blocks, yellow blocks, green blocks, and you have the freedom in an MBE system to create any combination of materials, well, physically possible, that you can dream of. There are many ways of generating X-rays, but the way these synchrotrons work is they have bunches of electrons rotating very close to the speed of light in a circle, in which these electrons, which are moving very fast, give off radiation, about 1 million times brighter than the intensity of light coming from the sun. So we can focus these high-intensity X-rays down to a few microns and use it to study both the diffraction, which gives us the structure, and the electronic properties of these new materials. Metamaterials are materials which are artificial, don't occur structurally in nature in that form. And the superlattices we are creating are also artificial materials which don't exist in nature, where we can control composition and structure very precisely to create new phases of materials which are not found in nature. What we're trying to do is to take the kinds of stacks you see in cell phones and come up with even thinner structures where you have, rather than a few microns thick of one material and the next material, you have 1 or 2 atomic layers of one material sandwiched between another one, thicknesses on the order of a few atomic layers. Currently, there's a drive to make many transistors on a chip to increase the density of the number of transistors you can put on a chip. And a lot of the efforts now has been to try to reduce their lateral dimensions. But being able to grow these materials as superlattices gives us a third dimension where we can also reduce the thicknesses of these materials in the vertical direction to make smaller, more efficient transistors.
Professor Kumar's work on applied experimental problems is complemented by theorists, computationalists, and other experimentalists working on a variety of condensed matter programs in the NC State Physics Department.